We're going to start this one today, which is another very big gear change. Right? We went from optics to thermodynamics. There's a big gear change right here. And now we're going from thermodynamics to what's known as electric forces and fields. Also a completely different topic. All right. And these are, of course, terms that we use every day. We've talked about forces. We're okay with that. But we have to give a slightly better definition, or a little more attention, let me say, to those forces. All right. Or to those terms I meant to say, sorry. All right, so before I get started with that, let me see if we have any questions on any of this so far. It's a very, very, very quick review of everything that we've done so far, including semester one. Okay.
Professor, I have a quick question. Did you happen to post the videos for thermodynamics, like the pre-recorded ones?
I think so, but I'm not sure. Are you not finding that on Canvas?
I didn't see any. I just saw them for 25 and 26, and then chapter 15.
Okay, if you checked recently, then I guess I must have forgotten. So I'm gonna go back and check. Thanks for reminding me.
No problem. Thank you.
Will the semester one material that you've outlined here be reflected on the first exam as well, or is this just to review?
Well, right now, this is just a review, but things like Newton's second law and our conservation theorems, all that stuff, that's always coming up at some point or another, right? So that's always good to have in mind. If you have forgotten the stuff from whenever you took semester one, it's not necessarily the previous semester. It wouldn't be a bad idea to go back and review the very basic things, including vectors. I would also say, if you've forgotten about vectors, as we'll see today, probably a good idea to go back and review a little bit about vectors, right? Right, any other questions? All right. All right, well, let's get started with our new fun and exciting stuff. Now, if we were meeting in person, we would be doing a couple of fun experiments, which unfortunately, I'm going to have to do the usual lame thing here and try to describe them. First of all, the term electric, we hear about it all the time, we use it all the time, but what exactly does it mean? Right. Experimentally, we find that if we take, let's say, a glass rod, a glass bar, right, and a piece of cloth, which I'm not going to try to sketch, and imagine that you have here just some bits of paper, pieces of paper. Right. Obviously, if I just approach a glass bar to some bits of paper, nothing much will happen. There may be, there's going to be a small gravitational force, but if you remember from semester one, the gravitational force is so small that it can't really be detected, or at least not very easily, right? But if instead we rub this bar with a piece of cloth, provided that it's a dry enough day, you'll find that these bits of paper will be attracted to this bar. They'll stick to it, right? But that will only happen if we wrap the bar with a piece of cloth. It's not going to happen otherwise. Or another experiment that we might have performed, we do the same thing. We take the same glass rod and we approach it to a pendulum that's made of a small aluminum foil ball sitting over here. And we'll find that if we do that, there's going to be a force acting on this aluminum ball. Depending on what you rub this with, you might have an attractive or a repulsive force. Right? And again, these are things that you can play with, you can experiment with. Right? But these phenomena happen only when you rub this with a piece of cloth. If you just bring a glass bar, nothing is going to happen, right? There's not going to be a force between the bits of paper and this aluminum foil ball. So we can ask, what kind of force is this? What kind of a force is this? Well, what forces do we know so far? Let me go back to the previous page and I'll come right back to this one. Well, here are those that we've seen so far, right? These are our candidates. Well, it's not a spring force. There's no spring anywhere. It's not a frictional force. There's no contact. It's not a buoyant force. There's no fluid. It's not a gravitational force because it's not there all the time. If you remember, gravitational forces are the most universal ones. They're always there and they act on everything. They don't just show up when you happen to rub a bar with a piece of cloth. It's not a tension. There's no string. It's not a normal force. There's no surface of contact. So it's none of these. So it's none of the familiar forces, none of the familiar ones from semester one. So the exciting conclusion here is that this is a new force, right? That's kind of exciting. Anytime you discover a new force, that's an exciting moment. Well, now the term electric is the name given to this force. This new force is given the name electric force. Right. Obviously, this is just a name. It doesn't mean anything. Right? We haven't discussed anything about this new force. We haven't stated any of its properties, but this is what we're going to do today. Now, interestingly, the electric force is not always there. If I didn't do this step, the electric force wouldn't be present. It shows up after I do this. So apparently the electric force is not acting on everything all the time. So we can ask, what does the electric force act on? What does this new force act on? Right, you might remember that gravity acts on everything all the time. There is nothing that is immune to gravity. We had those other two forces, the nuclear forces, those only act on subatomic particles, and not even all of them, some of them. Right? So those are very limited in scope. They're very important, but we don't experience them directly. What about this new electric force? What does it act on? Obviously, it's not just the bar or just the bits of paper because that force is not always there. It appears when I take an extra step. Right? By the way, in a real, if we had an actual meeting in person, we would also probably be doing the Van de Graaff generator experiment where you got sparks flying back and forth between charged spheres. Unfortunately, well, we're gonna have to try to imagine it here. Right. Right, so what does this thing act on? Now, if you go back to the very beginning of semester one, the very first thing that we talked about, or if you did it somewhere else, the first thing that you should have talked about there is the indefinable quantities, which are our starting point. And if you remember, we decided to use as our indefinable quantities mass, space, and time. Right? And then we started writing down definitions. We started writing things like displacement, velocity, and acceleration, forces, all that fun stuff. But it was all based on these three indefinable primitive quantities. If you prefer, you can call them the primitive quantities, our starting point. Okay? Everything we did in semester one was based on all that. We take this for granted because it's not very easy to break them down into simpler things. I don't know how to describe space. I can see it, it's right here, but I don't know how to attribute it to anything simpler. I have a vague idea of what mass is, right? The more something is, the more difficult it is to push it around, right? I kind of have an idea what time is. I just don't know how to simplify these any further. So I'm taking them as indefinable, and I'm taking them as my starting point. Everything else is based on that. Well, now we have to add one more element to this list. That's the worst plus sign I've ever seen. We have to add one more indefinable to this list, which we're going to call electric charge. And typically we get lazy and we drop the term electric and we just call it a charge. Strictly speaking, that's not right, but it's fine. We can get away with it. So we probably will, right? This is the stuff that the electric force acts on. This is what electric forces act on. Of course, that's not really an explanation because we haven't decided what electric forces are other than a name that we gave to forces that we observe sometimes. Right, so we take this to be another indefinable quantity in this list. So it's a new entry. So what is charge? Well, it's just something that exists and we don't break it down into anything further. Right? Now with further experiments, with more experiments, we can figure out a few experimental facts about charges. We find that there are two types of charge. Which for convenience and rather arbitrarily are called positive and negative. Although there's nothing inherently positive or negative about either one of them. These are names, right? Interestingly, there are two types, not 3 or 4 or 1, right? Somehow it just happens to be 2. Would I know that without experimenting? No, of course not. I would have to perform experiments in order to know these things, right? Experiments are required. Otherwise, I would not know that there are only 2 charges. Maybe there would be 1, maybe there would be 100, I don't know. But it happens that we have only 2, and we call them positive and negative. Right? And charges exert forces on other charges. Oops, sorry. I am not doing well today here. Charges is seen that charges exert forces on other charges. Which is what we call electric forces. The name electric is a name we give to this type of force, right? By the way, when I say more experiments, I mean more experiments of the type that I tried to describe earlier, more, fancier, more sophisticated experiments, but basically the same thing, right? All right. Now, what does this force look like? The easiest place to start describing this force is what's known as Coulomb's law. And of course, just like any other law, it's an experimental fact. There is no way I would have known that unless I did the experiment, right? And this is most easily stated by looking at point charges. Just like we had point masses in semester 1, now it's convenient to think of point charges. Let's take 2 point charges, and for no particular reason, I'll make them both positive. Let's call this one Q1, and let's call this one Q2. For some reason, Q is a very typical letter when we discuss charges. Now, these are supposed to be points, not extended objects, which means they define a unique line, straight line between them, right? It's a postulate of Euclidean geometry that there's only one straight line that goes through any 2 given points. So there's no ambiguity here. There is a charge, there's another charge. There's going to be an electric force sometimes also called the Coulomb force. Known as the electric or Coulomb force. Right. This force has fundamentally established properties. First, the electric force is always directed along a line joining the two charges. Along a line. Remember, those are points, the two charges, joining the two charges Q1 and Q2. Right. This force is attractive if Q1 and Q2 are opposite. That means if Q1 is positive and Q2 is negative, or the other way around. And is repulsive if Q1 and Q2 are like, they have the same sign, they're both positive or both negative. Right. The magnitude of this force is directly proportional. That means directly proportional, right, to the product of the two charges. But because one of these could be negative and magnitude can't be negative, I have to take absolute values. And the magnitude of the force is inversely proportional to the separation between the two charges squared, where the separation between 2 points, of course, is uniquely defined, right? There is only one distance between any 2 points, at least in a Euclidean space, which is all that we're going to care about here, right? Again, these are all experimental facts. There is no way to know any of that without experimenting, right? Notice the first two statements refer to the direction of the force. Last two statements refer to the force. How do I write the magnitude? These are proportionality signs, and proportionalities are fine, but we prefer equations. We'd like to have magnitude of the force equals something. So if I want to replace the proportionality with an equal sign, I need a coefficient of proportionality, right? So now I want the proportion to be equal to, and here's a little space. I have the product of the two charge absolute value in the numerator, the separation squared in the denominator, and typically denoted by this lowercase k, which is known as the Coulomb constant. Presumably, it's a property of this universe that we happen to be in. Right. This thing, of course, will have a particular value depending on the units that you're using. Also notice here that we have to have a way to measure charge. How do we measure charge? Well, the same way we measure mass. We just take a charge and we call it the unit, and we compare everything to that. In the international system, the unit of charge is 1 Coulomb. This guy's name is everywhere. Right. And the Coulomb constant in the international system has an ugly value, 8.99 times 10 to the minus 9. Well, let me verify that. I never remember these numbers. I always have to look them up. 8.99 times 10 to the, sorry, not minus 9. That was very dumb. It's plus 9. That I actually knew, but that's a typo over here. There's no minus. It's plus 9. And the units are newtons meters squared per coulomb squared. Right. This is the magnitude of the electric force between any 2 point charges, Q1 and Q2, separated by a distance r. And here's an ugly number that goes in front of that equation to make it work in the units that we've chosen. Okay. Sometimes this expression here is called Coulomb's law, but remember, this is only giving you the magnitude. Coulomb's law is all these four statements. We also need the direction for a force. Right? Now, in a strange sense, this is pretty much the entire chapter. There is more material, but it's all based on this. So let me pause here for a moment and see if we are all okay with that. Do we have any questions or any comments? Everybody okay with that? All right, and if you're wondering where this comes from, well, this is an experimental fact, just like any law, right? You have to perform a bunch of experiments and eventually you figure out that that's how things behave. Amazingly, this is not a terribly complicated equation, right? I guess we're very lucky things are that simple. This could have been an awful expression, maybe even impossible to write down in the form of an equation. In our universe, that's how things behave, thankfully. All right.
I have a quick question.
Question, yes.
So I think I just missed it, but what does the Q in brackets equals C mean?
This is the unit of charge, the standard unit. Remember this notation? Put anything in here. This means the SI units of whatever is in the brackets. Oops, what am I doing?
All right, that's what I thought. Thank you.
Units of whatever is inside there. Right. Good, any other questions? All right. Now, what do I do if I have a bunch of charges? Suppose I have, let's say, a charge big Q over here. I have a charge Q1 over here. I have a charge Q2 over here, and I have a charge, let's say, Q3 over there. How do I find the total force on big Q? Well, I can consider the interactions in pairs. Big Q is a charge in the presence of three other charges. So there's going to be three separate interactions. There's going to be a force from Q1, little q1, which I can write as F1. There's going to be a force on big Q from little q2. Let me call this force F2. And Q2 will also be acted by Q3 with the force F3. And of course, the total force is the vector sum of the individual forces, right? So the interaction between Q1 and big Q, since big Q is positive, Q1 is negative, there's going to be an attractive force in this direction. I can call this force F1. Now look at the interaction between big Q and Q2. They're both positive, so there's going to be a repulsive force along the line joining the two charges. I'm making up the magnitudes here because I don't know how big these charges are. But we're not interested in detail here. We're just interested in a little intuition. And then there's going to be a third force acting on big Q due to Q3, which will also be an attractive force. So it's going to look something like this. Let me call this one F3. Right? And I have to add these up as vectors. Everybody okay with that? Now, of course, every charge will act on every other charge. Like Q1, for example, will also experience three different forces. But here we're asking, what is the force on big Q? That's why I'm only drawing these vectors. If we were asking what's the force on little q2, well, there would be one due to big Q like this. There would be one due to Q1 like this. There would be one due to Q3 like that. Well, that's a different charge. Here we're asking what the force is on big Q. And this is why I was saying this is probably a good time to go back and review vectors a little bit in case you forgot from semester 1. And speaking of that, let's do an example. We practice our vectors a little bit. Let's say we're given the following charge configuration, charge distribution, which is just a fancy way of saying I've got a bunch of charges and I just place them in different locations. So we're given a coordinate system, x, y, and let's put a charge at the origin. Let's call it Q1. Let's make it positive and call it Q1. Here I was trying to say that this charge is positive. I guess I'll put the plus sign outside. Let's take another charge and put it up here. Also positive. These are all point charges. Let's call this one Q2. And let's say it's half a meter away from the origin. And then let's go out this way another half a meter and put another charge, which will also make positive, and call it Q3. And let's say that all three of these charges have the same value. This is not mandatory, but we don't really care. We just want to make the problem simple. Let's say, 2.9 microcoulombs. By the way, I should say that the coulomb is a rather large unit. So we typically see fractions of a coulomb, microcoulomb, nanocoulomb, things like that. And you might remember that micro means 10 to the minus 6. So before I plug this value into any calculator, I have to convert it to standard units, which are coulombs. So somehow we got hold of these charges and we placed them like this on three corners of a square of edge half a meter. And the question is, find the total force on charge Q3. Okay. It's a fairly simply stated question, but the problem is not exactly obvious, right? It does take a little bit of work. All right, so where do I start from? Well, I might start by asking, why is there a force on Q3 in the first place? Why should I say that this is anything other than 0? Well, Q3 is a charge. There are a bunch of other charges in this picture, namely two other charges. Each one will interact with Q3 separately, independent of the other charges. And also notice that there are no springs, no frictional forces, no motion. Right? So there are no other forces. These things are not assumed to have any mass, so there's no gravitational force. Even if there was a gravitational force, it would still be negligible compared to the electric force, but there's none of that. So the only forces here are electric forces. And I'm only interested in finding the force on Q3. What is the force on Q3 due to? Well, first of all, there is an interaction between it and Q1. So the net force on Q3 will have to be made up on the force on 3 due to 1. I'm going to call it F1. And then there is a separate interaction between Q2 and Q3, which will produce another force that I'll call F2. Right. What do these vectors look like? First, I'm going to look at the interaction between 1 and 3. I'm ignoring Q2 for the moment. Well, this force, since both of these charges are positive, the force has to be repulsive and it has to be along this line. So my only option is this force, which I'm going to call force F1. What is the magnitude of force F1? Well, according to Coulomb's law, is the ugly constant K times the product of the two charges involved in the interaction. Here, I don't really care about the absolute values because everything is positive, but let me be a little more formal. divided by their separation, let me call this R1, squared. How much is this? Well, I'm noticing that this is a right triangle, and the distance I'm looking for is the hypotenuse, and I need it squared, which is good because the Pythagorean theorem says that the square of the hypotenuse is the square of this side plus the square of the other side. In this case, they both have the same value, but that wouldn't matter. So this is 2 times 0.5 squared. And I don't even need to take square roots because that's what goes down here. Now I know everything here. I know K, it's that ugly number 8.99 times 10 to the 9th. We know the charges, and we know the distance between the two charges. So I can plug everything into a calculator. If I do that, I will find 0.151. What units is that? Well, since everything is in standard units, that should also be standard units, which is newtons for force. So I got the direction of this vector and I got its magnitude. Everyone okay with that? All right. Well, now what about the interaction between Q2 and Q3? Well, they're still both positive. So there's going to be a vector force acting on Q3 that is going to be repulsive, and it has to be along this line. So the only option is this vector. There's no ambiguity, right? That's my only option, which I'm going to call force F2. What is the magnitude of F2? Well, it's the same ugly constant K. The product of the two charges involved in this particular interaction, which is Q2 and Q3, divided by their separation squared. But here the separation is just 0.5. Sorry, I forgot to close the absolute value here. 0.5 meters squared. And if I plug this mass into a calculator, I get 0.302 newtons. Let me make sure of that because I'm having a hard time reading my own handwriting. Yeah, that looks okay. Everybody good so far with this? All right, now I found the two individual forces. Remember, I'm looking for the net force. So I have to add those two. So if I add these two together, I get a 3 at the end, I get a 5 in the middle, and then I get a 4 next to the decimal point. No one is going to complain. This makes absolutely no sense. First of all, the equation itself doesn't make any sense. I have a vector here, and I have a number there. The two can't possibly be equal, right? This is completely absurd, what I wrote here. No one said anything. So what do I do next? That's not right. That's obviously, it can't possibly be that a vector is the same as a number, right? There can't possibly be an equal sign between a vector and a number. My next step. Any suggestions?
Determine the direction
Very good. How would I do that?
with the negative sign.
Negative sign where? I'm not saying you're wrong. I'm just asking where you would put the negative sign.
In front of the both newtons because they're repulsive.
Well, be careful. The vectors here, the forces are repulsive indeed, but remember these are vectors. They're not positive or negative, right? Instead, how do I deal with vectors? What's the easiest way to deal with vectors? We could do it graphically. Remember how to add them. I have to complete this parallelogram and draw the diagonal. And that would be the total force Here it is. So all I have to do, if I'm very careful about sketching, all I have to do is measure the length of this vector and measure this angle, and there's my answer. But that's at best difficult, time-consuming, very tedious, and also very prone to errors. Instead, how do we add vectors? Nobody remembers that from semester 1? Nobody remembers components? That's the easiest way to do it, right? So I'm going to go to components. The problem is already giving me a coordinate system. So I'm going to say that the x component of the total force on charge Q3 is the x component of the force F1 plus the x component of the force F2. And of course, the same for the y component. So now I don't have arrows, I have numbers, which are a lot easier to deal with. Right? And all I have to do is figure out what these components are. So let me go here to the side and first break down the vector F1, this vector, into its x and y components. What is F1x? What is F1y? And then I want to do the same with F2. What is F2x? What is F2y? Well, here's vector F1. What's this angle here? Let me call this angle phi so that we don't confuse it with that theta. That's the same as this angle. What is it in this case? That's the worst phi ever. It's very difficult to draw a phi apparently. Well, remember that the tangent of this angle phi is the opposite over the adjacent, which means that phi is the inverse tangent of the opposite over the adjacent. Well, in this case, the opposite and the adjacent are both 0.5. So we don't even need a calculator. What is this angle here? Since both this and that are the same. Nobody helps. 45 degrees, right? And this is half a meter, so is that. So this is a square. The angle between the diagonal of the square and one of the sides is 45 degrees. But even if we weren't lucky and these two numbers weren't the same, we can always plug them in here and find what this angle is. And now I can project this vector into the x and y axis. What is the x component? What is the magnitude times the cosine of the angle phi, which is 45 degrees. I don't need a minus sign here in the front. If I plug this into a calculator, this will give me 0.107 newtons. What's the y component? What's the magnitude times the sine of phi? Of course, for 45 degrees, sine and cosine are the same. So this will also be 0.107 newtons. This will go here, that will go there, right? What about vector F2? Well, that one is easier because it's all lying on the positive x-axis. So the x component is just the magnitude of F2, which we have here is 0.302 newtons. And the y component is 0. So this will go here, and that will go there. So the net force, component x, is this plus that. So that's a 0.409 newtons. Okay. And the y component is this plus that. So that's a 0.107 newtons. Here are the x and y components of my total force. Strictly speaking, that's it. We're done with this problem. There is the vector. We got its components. And we're done. Sometimes a problem says, don't give me components, give me magnitude and direction. Well, you might remember from semester 1, that's an easy extra step. The magnitude of the force is the square root of the x component squared plus the y component squared. And if I plug that into a calculator, I should get 0.423 newtons. And the angle theta, this angle here, is the inverse tangent of the y component divided by the x component. So I'm kind of cramming everything here together of the y component divided by the x component. And if I plug that into a calculator, I'll get approximately 14.7 degrees. So either the components or the magnitude and the direction, right? If the problem says, give me the components, I'm finished here. If the problem wants to be a pain and says, don't give me components, but give me magnitude and direction, well, that's an extra step, which is very standard. And again, remember that if you forgot about this stuff, go back and review some of it from chapter 1. All right, well, that type of problem is not really a whole lot of fun. It's a bunch of algebra. But I wanted to do one sort of in detail because we may have forgotten a little bit about manipulating vectors from semester 1. Right, let me see if we have any questions. Everybody good with this example?
Can you go over how you calculated F1 and F2 again?
The magnitudes here?
Yes.
Yeah, this is using Coulomb's law, right? We want the magnitude of the force, which is Coulomb's constant, that ugly 8.99 whatever number, times 10 to the 9th.
Right.
The product of the two charges, that's this thing, squared, of course, because it appears twice, divided by the separation squared. Well, the separation between 1 and 3 is the hypotenuse of this right triangle. So this squared is this squared plus that squared. Since both are 0.5, this number is 2 times 0.5 squared. Plug them into a calculator, you should get this. Same thing for the interaction. Sorry, go ahead.
How is that the radius again? You need the radius for this square or for the hypotenuse?
Well, you need the distance between the charge Q1 and the charge Q3, right? Which is the hypotenuse of this right triangle.
Right.
Right?
Okay.
Does that make sense?
Mm-hmm.
Very good. And the same for the other two charges, but now these two are separated by half a meter. So I don't need to do a Pythagorean theorem. There it is. And of course, don't forget the square. And these two charges are, again, each one of them is this value.
So is R in reference to the distance between Q1 and Q3, or is like the radius of the distance between Q1 and Q3?
Well, there's no such thing as the radius of a distance, right? It's 2
Sorry,
points.
my bad. My bad, halfway.
Right. Well, you don't have to confuse r with a circle here. This is just a distance, right? It's just a distance
Okay.
between these 2 points. Each charge is a point,
Gotcha.
and between the two there is one unique distance, which I use the same thing that the book uses. The book calls it r, so I don't want to change the notation as much as I can. But yeah, there are no circles involved here, right?
Yeah. Sorry, that was my mistake.
That's fine. That's fine. It does get a little confusing. There are a lot of symbols here. So yeah, no problem. Very good. Other questions? All right. All right. Now, obviously, I don't want to be doing this if I have 15 charges, right? Can you imagine trying to find the force of 14 of them on one? It's going to be very old very quickly. Now, there's one way to get around this difficulty, which also involves a difficulty of its own. And that brings us to a new topic known as the electric field. And let me first remind everyone what a field is. We talked a little bit about this in semester 1. A field is a region of space. Right? It can be one-dimensional, two-dimensional, three-dimensional, n-dimensional. It doesn't matter. Anything can be a field as long as it belongs to a space. Right? A vector field, is a region of space with a vector attached at each point. And probably the easiest vector field that you can visualize is the gravitational field where you happen to be right now, like in your room. You're probably in a room right now. That room is a field, it's a three-dimensional field. It's a region of space. At each point, you can think of a vector that points straight down and has magnitude 9.8 meters per second squared. Right? That's a gravitational field. That's a good approximation, maybe I should say, of the gravitational field of the room that you're in. At every point, there is a vector pointing straight down with a magnitude 9.8 meters per second squared. Of course, there is an infinite number of points, hence there is an infinite number of vectors, one at each point. Right? Everybody okay with that? Oh, I made another error here. Why isn't anyone correcting me? I made a lot of typos. Field, forgot to write this letter, L. All right. Now the electric field, which we're going to denote by an uppercase E with a vector on it, refers to not a gravitational force, but it refers to an electric force. We could look at the interaction between two charges. Let me make this one big Q, and let me make this one little q. And let's make little q negative just for fun. All right, again, these are point charges. They are defining one straight line. And of course, because big Q is there, little q is going to feel an attractive force towards big Q. Same thing, of course, for big Q towards little q. Right? Because now they have the opposite signs. So one way to view this interaction is to say that Q exerts a force, which we call the electric force. Big Q exerts a force on little q. And of course, the other way, little q exerts a force on big Q, which kind of comes up against the same problem that the gravitational force did. All of a sudden, somehow, this little q is supposed to know that big Q is there. This distance between them could be very large. Right? We're assuming, by the way, that every charge is fixed, right? They're not moving around. They're nailed to the paper or the screen or whatever you happen to be writing on. Right? All charges are at rest. Right? So somehow little q knows that big Q is there. And you might ask, how does little q know that big Q is there? And that's actually a very good question. It's a very simple question to ask, but it's not by any means obvious how to answer that question. One way to answer that question is to view this interaction somewhat differently. So instead of saying that all of a sudden just forces appear, you can say that big Q generates an electric field which is there regardless of whether little q is brought at that point or not. Field, let's call it E, and let me give it a little subscript here, uppercase Q. And this E sub Q acts on little q, producing the electric force. Right? We know what the magnitude of that force is. We also know its direction. We know that the magnitude of that force is K times the product of these two with an absolute value to avoid any negatives divided by the separation squared. Well, now imagine we throw this away and instead we bring a Q prime. And let's make it positive this time. Well, this one is going to feel a repulsive force from big Q, which will have exactly the same magnitude. The only difference is that I'll have to replace this with a Q prime. Everything else remains the same. If I look at this expression, this part of the expression is geometrical. There is this R squared here, there's that distance. It depends on big Q, which we're thinking of as the source of this force. And there's a constant here that tells us that we're in this particular universe. This constant could be something else in another universe, but since we are here, we don't really care about that. We can leave this constant as it is. So in order to find the new force, all I have to do is just remove this little q and instead use this little q prime. So what remains here is what I'm going to call the magnitude of the electric field generated by big Q. Another way to see it is you can think of these as test charges. Typically, we want the test charge to be positive, but that doesn't really mean very much. Test charges. What do I mean by test charges? Well, suppose there's nothing here. There's only this big Q. And maybe this big Q is very far, I can't see it. How would I know that there's an electric field at this point? Well, I can go to the back room, the supply room, grab a handful of charge and put it over here at this point. Is there going to be a force acting on it? If so, then I know that I have an electric field because electric fields act on charges, right? That's how I would detect an electric field. And let me also give you a simpler example. How do you know there is a gravitational field in your room? Well, you can grab a mass, I don't know, say your pen, and put it at a point, place it somewhere, and you'll find that there's a force acting on it. Gravitational forces act on masses, hence there is a gravitational field at the location of your pen. Well, here I don't have a gravitational force, but I have a similar force, which I called electric. And for that, I need a charge in order to detect that force. So I'm going to grab a test charge. I'm going to go to the supply room, grab a test charge, put it over here, see if there's a force. If there is a force, then there is a field. I would like for the field due to this charge to not depend on the test charge. I could have, someone else, maybe you're doing the experiment, you could have grabbed a different test charge. But we want our answers to be the same because otherwise it would really, there would be no point. So let me go to the next page and formally define the electric field. The electric field is defined as the force that acts on a test charge that you happen to choose placed at a given location divided by that test charge. By dividing, we remove the dependence on this test charge. We don't want our answer to depend on whatever we happen to choose as a test charge. Because I grabbed the test charge Q, you might do the same experiment, but you could have grabbed a different charge, Q prime. We still should be measuring the same electric field. So we divide the test charge out in order to make this quantity independent of this test charge. This equation is very simple, but very important. Right? This is a defining expression of the electric field. How do I know there is an electric field, say, at this point? There is a point P. Notice there's no charge there, right? It's just a point. So I want to ask, is there an electric field at point P? How would I know if there's an electric field at point P? I would pick a test charge. I would place it at point P. Let me call the test charge little q, which for practical reasons we want to think of as small and positive. There's nothing wrong with a negative test charge, but if you look at this expression, if I use a negative test charge, these two vectors will have opposite directions. That's fine, that's not a big deal, it's just an extra complication. There's really no reason to overcomplicate our lives. So let's just make the test charge positive so that E and F sub Q point in the same direction. And why do I want it small? Well, because if I use a very large charge and I put it here, I might disturb whatever is producing the electric field at this point. So I want it to be as unobtrusive as possible. That's why I want a small test charge. So pick a test charge Q, small and positive for convenience, place it at point P. Remember, there's no charge here, but we can imagine placing one, right? Is there a force on little q? Well, if so, if there is one, then the electric field at point P is defined as that force on little q divided by little q, so that we can remove the dependence on our test charge. If you think about this, this is how you would determine whether there's a gravitational field where you're sitting, right? Instead of a charge, you would take a mass. You would measure the force on that mass, and then you would divide out by your test mass, because you don't want the result to depend on your test mass. For gravity, it doesn't matter, but that's a different topic, an exciting one, but not really relevant to our purposes. All right. Everybody okay with that so far?
I have a question.
Question, yes.
So for the FQ, like the F little q, that would be using the formula like the Coulomb's law, where it's like K, then Q1, Q2 over R squared.
Right, yeah, if these are point charges, but the electric fields could be produced by other things that are not point charges. If they are point charges, then yes, that's right.
So
Very
if
good.
it's not a point charge, how would we find FQ?
Yeah, that's a very good question, and it's by no means easy. We're going to talk about a method for doing that in some cases next time. But for now, we're just looking at point charges. Now, if you don't have, actually, that's a very good question, so let me very quickly address it. What if you have a charge distribution, you have a blob? This is big Q. Let's say it's smeared out. I have a blob of positive charge, and then you have your little test charge there. How would you find the force on this due to that? As you can see, that's not exactly a trivial problem. One thing you can do is break this up into a lot of small volumes. A little volume delta V sub I, which will include a charge delta Q sub I. You can find the force from this, thinking of it as a point charge. Then you can go to the next one, do the same thing, go to the next one, do the same thing, and so forth, and add all that stuff up. As you can imagine, that is not easy, right? But in principle, if you have a non-point charge, if you have a charge distribution, a blob of charge like that, you can think of it as broken down in small pieces And if the pieces are small enough, you can think of them as point charges. But then, as you can imagine, this becomes a very difficult calculation. I have to add all these forces, which at best is difficult. Sometimes it's just too difficult, so we can call it impossible. Does that address your question before I go on?
Yes, thank you.
Very good. Now we'll see next time that there is a way to get around this difficulty if we have enough symmetry. We'll talk about that next time. For now, let's just stick with point charges. That was a good question, though. Other questions? All right. Now let's try to think about the electric field due to a point charge. Let's call that point charge big Q. So let's put it over here. Here's big Q. So this generates an electric field. It's a point charge. I named it positive for no particular reason. All right. So what does the electric field look like? Well, I have to imagine if I want to go to a point, and I want to imagine that I put a positive test charge here, small test charge. What kind of a force will this feel? Well, it's going to feel a repulsive force away from big Q. Right? If I move this charge further away, but along the same line, I will get a force in the same direction, but smaller in magnitude. If I move it closer, I'll get a force that's larger in magnitude. And the further away I go, the smaller the magnitude becomes. I could go on a different line and do the same thing. Imagine that I put a test charge here, positive test charge, it'll feel a large repulsive force. As I go further away, the force will become smaller in magnitude, but it'll stay radially outward. Of course, this is a completely symmetric situation, so you can imagine just rotating this picture. I can't draw an infinite number of vectors, but I can draw a few of them. Right? So we find that the electric field due to big Q is radially outward for Q positive. And of course, the magnitude of the field would be the magnitude of a force on an imagined test charge divided by the charge itself. Sorry, not R, that's a Q. Which of course by Coulomb's law is given by K times the absolute value of Q divided by R squared. So here's the magnitude of the field, and here is its direction. Now we don't have to do this every time. From here on, whenever we see a positive test charge, we can imagine an electric field pointing radially outward. At each point, at distance R away, that's the magnitude of the field. Notice that there's no need for a charge to be there. You can imagine one being there if it makes it easier for you, but there's no need for a charge to be at this point. This is a point, not a charge. But you can imagine that you're placing a little test charge over there, little Q, right? And obviously I didn't draw an infinite number of vectors because I can't do that. I only drew a few vectors. Everybody okay with that? Now, how would this picture change if this charge big Q was negative? Any suggestions? So let me go to the next page and take a negative big Q. How would this picture change?
It would go inward.
Very good, excellent. It would be exactly the same, but all the arrows would be flipped. Very nice. Excellent. Very good. The field of a negative charge points radially inward. So the electric field due to big Q is radially inward. The magnitude remains the same. it's still the ugly constant K times the absolute value of the charge divided by how far away you are from it squared. Very good, excellent. Everybody okay with that? Well, this is not a very good picture, but you'll find much better ones in your book. Same magnitude, but now all the arrows point in the opposite direction. Let me very quickly summarize what to retain from this discussion. The magnitude of the electric field produced by a charge big Q, if this is a point charge, it's K big Q divided by how far away you are from the charge. The defining equation for an electric field is take a test charge, put it at a point, find the force acting on it, and divide the test charge out. And remember that electric fields are generated by charges. By charges. And they act on other charges, producing what we call the electric force. It's this expression solved for the force. So the force on a little q that's placed in an electric field, what a terrible arrow up here, is q times the electric field at the location of the charge. All right, so this is a little brief summary. Probably the most important points that we discussed today. Is this okay with everyone? Any questions, any objections? Good. Next time we'll talk about some more fun stuff relating to electric fields. Until then, have a good evening.
Thank you.
Thank you all. Enjoy your
Thank you.
evening.
Professor.
Thank you.